Okay. Okay, good morning. Several of you already know me, right? You know me? Anyone else? No one else? You know me, right? Okay. My name is Zhou Xianzhou. My office is in this building, 318C. My email address is zhouxianzhou.zhou@usm.edu. You can go to the USM website and find my confirmation. And we have a website for this class. The address is http:// you go to my website, and on the left-hand side, you click teaching, and you are going to see the courses I'm teaching this semester. And you click the CET316. It will ask you a password. The password is digital. That's the password. Then the syllabus and the homework will be on the website. This course is 2 credit hours. There's another separate labs, which is 1 hour, and we are going to do the labs later time, maybe after 2 weeks. And for these 2 hours, each meet is 90 minutes, right? So we are going to meet, anyone has calculated that? We won't study until the end of the semester, because this is only 2 hours. I calculated, it's like 15 lectures plus 2 midterms, then plus a final. So that's totally like 18 class meet. So that is for 2 credit hours. For 3 hours, that will be 25, then plus 2 midterms, then plus 1 final. So we are going to about 15 lectures, then that's it. So the time is Monday, Wednesday, it's today, from 8 to 9:30, and the textbook is Digital and Analog Communication Systems, the 8th edition. And all this information is on the website. You can click the syllabus. Anyone got the textbook? It's supposed to be in the bookstore. Anyone has the textbook? Not yet? Right. Next one, we are going to discuss the major topics, give you a brief introduction for the class. This is digital communication. There's another class is called Analog Communication Systems, which is required for EET student, not required by CET. Anyone from here are EET? EET. You're EET, right? Have you taken 315?
Took last semester.
Last semester. Okay. Anyway, all others are from CET? Alright, that is good. Okay, CET. The first chapter is the fundamentals. We discussed the trigonometry, the mathematics, and signals and systems. So this is the same for both classes. The second chapter is modulation and demodulation process. Modulation, demodulation. That's also the same for these two. The next one is sampling theorem and post-modulation. That is for this class. The sampling theory means we convert analog signal into a digital signal, in discrete time signal. And the next one is digital data transmission. We come to the digital part. And the next chapter will be encoding technique and error detection and error correction. And the last chapter, if time permits, we are going to discuss data communication systems. Next one, we are going to briefly discuss the topics that will be covered in this class, so you can have an idea what we are going to study in this class. Right? The first, chapter 1 is the fundamentals. Fundamentals, we are going to discuss several trigonometry identities. For example, cosine function times cotangent function. I believe you already have this math 103. And the next one, we are going to discuss the concept of a power, fundamentals, trigonometry. And the next one will be electric power. If you are given a signal, you need to know how to calculate the electric power. The next one will be time domain and frequency domain representation of signals. So we already know in circuit analysis, if you are given a time domain signal, that means the signal is a function of time. We can observe the signal with the oscilloscope. On the oscilloscope, it look like this. For example, sinusoid function, that is t, and this one is no matter voltage or current. So that is the time domain representation of the signal. Suppose if this is a perfect ideal sinusoid function, which extended to infinity on both sides, then we know this one has a singular frequency. For example, the power here has only, what's the frequency here? What's the frequency on this outlet? Do I know the frequency? What's the frequency over here? We know this is cosine or sine function, right? What's the amplitude? Right? We know the RMS value is 110, right? So the amplitude equals 110 times the square root of 2. What is the frequency? 60 hertz, right? Still sleepy, right? This is 60 hertz, right? So it's 60 hertz. So we know this is 60 hertz ideal sinusoid function. If we look at the same signal here with in frequency domain, that means we have this in frequency f, right? And this one again, no matter current or voltage, this is amplitude. Then we know we have only singular frequency, so which is 60 hertz. If we use the hertz as a unit, then the signal will be look like this. So that is called the frequency domain representation. These two representations are to represent the same signal. So they must have some relationship between these two. Right? They are related by Fourier transform. Right? If you are given this signal, we can use the Fourier transform to get this signal. If you are given this signal, then we can use the inverse Fourier transform to get this signal. The concept of Fourier transform and the inverse Fourier transform will be discussed in 323, signals and systems. But in this class, you only need to know they are identical, but they are different representations. One is in time, another one is in frequency. They are the same thing. We are going to use this time domain and frequency domain representations to discuss the basic concept of modulation and the demodulation process. For example, the AM, amplitude modulation. What does that mean in time? What does that mean in frequency? So we are going to discuss the details later. Next one, once we know how to do the modulation and the demodulation process, we are going to discuss the systems or the circuit, how to do this, to implement this in labs. That will be the AM realization method. The next topic, this is the AM. The next one will be like FM. In AM, the information is in the amplitude. AM means amplitude modulation. The information of your signal is in the amplitude. The FL means frequency modulation. Everybody knows this, what FL means, right? You know that. You drive your car, right? You listen to the radio, it's FM radio. That means frequency modulated. What does that mean? That means the music, which is baseband, the music, the frequency is from 0 to about 20K. It's a very low frequency. But the FM station is, anyone knows a typical FM station, the frequency? What's the frequency? You listen to a radio station. What station? 90, for example, 90.5. That is megahertz. But the music is only less than 20K. So definitely, the signal from the FM station is not the music. At least not directly the music. So that we use the FM technique. So that means the contents of the signal, or the music in this case, is in the frequency of the signal. So that is FM. Another similar scheme is called PM. The signal is in the frequency, is in the phase of the signal. We are going to discuss the modulation process and the demodulation process. Modulation process means how you transmit your baseband signal, your music, your voice through these high frequency signals, which are called carrier signals. So transmit. When we receive that, we are going to need to convert back to the baseband signal so we can hear the music. Human beings cannot hear the 90.5 megahertz frequency. Have you tried any? When you do the AC circuit labs experiment in the labs, we have a signal generator. You can listen to the signal, for example, 1 kHz, you can hear something. How about 100 meg? You cannot hear anything. So human ears cannot hear very high frequencies. So that means once we receive all these signals, we need to have a scheme that convert these high frequency signals back into the baseband signal, so we can use that signal. The next one will be QAM modulation, quadrature amplitude modulation. If you buy the TVs, there's at the menu at the back somewhere, that's QAM. It can transmit 2 signals with the same carrier frequency. The next, like SSB, VSB, and all of these are different modulation and demodulation schemes. All these are analogs. And also for digital signals, we have ASK, FSK, and PSK. That's amplitude shift keying. It's also called digital AM. That's a frequency shift keying. You can call this digital FM. This one digital PM, something like this. It's called phase shift keying. Also, we are going to discuss modulation and demodulation process. Okay. So those topics will be in the second chapter. This is chapter 2, analog modulation and the demodulation process. Okay. We are not going to discuss a lot of details. For example, how to implement this in the labs with the circuit will be discussed in 315, which is analog communication systems. In this case, we want to discuss the ideas. Because the major topic we are going to discuss in this class is digital transmission. We use this as fundamentals. The next one, chapter 3, will be a sampling theory. Sampling theory means we know the signals, most of the signals are analog signals. For example, you go to the concert, listen to music. The music is analog. And my voice here is analog. But if we want to transmit through your phone, most of the phones are digital phones, right? We need to convert this analog signal, for example, like this, into a digital signal. The first step is to convert the analog into a discrete. Then the next one is digital. So from analog to discrete, this process is called sampling. Through sampling, we got discrete. So how to do this? we are given this analog signal. Then we just take, for example, some samples. Usually we use uniform sampling. That means for each second, we get one, or each microsecond, or each millisecond, no matter. That's called sampling period. But anyway, the period are uniform. So this is called uniform sampling. In this class, we discuss only uniform sampling. And this period is called the sampling period. That's called T. And 1 over T, that's called the sampling frequency. If the sampling frequency is large, that means you sample this very fast. If the sampling frequency is small, that means you sample this very slow. Once we get this sampled data, for example, here, this may be 1, this may be 2, this one may be 3, this one may be something, okay? This is negatives, some values. We are going to, this is called discrete value. The next step will be converting into a digital signal. Digital signal is only zeros and ones, right? And because, for example, in the CD, we can only store 0 and 1s. We do not have anything else. So we are going to store all this digital value, and we need resources. So you may wonder, how many data should we store, for example, for 1 hour for music? For example, from here to here, this is 1 hour of analog signal. How many data should we store this? For saving, we want to store as less data as possible. For example, okay, you store only this one. You store this only one in the CD, then you play it, okay, you hear a perfect 1 hour music. That looks too good to be true, that is impossible. For better quality, we can imagine we want to store as many data as possible, but you are going to need a large storage. For example, maybe 1 disk or 2 disks or even more. So there's a balance between this. So how fast, what is the sampling frequency? How fast, how large this fs should be chosen to, so we can sample this, then later time reconstruct the signal so we can still recover the original analog signal without information loss. That is the sampling theory. We are going to discuss how to derive the sampling theory from the concept of the modulation and demodulation process. To be brief, the sampling theory means if we know the frequency, the highest frequency in the analog signal, for example, the music, which is 20K, then we can sample this with at least twice as high as this frequency. For example, we can use 44.1K. That is at least twice as the highest frequency in the analog signal. We can use this frequency as the sampling frequency. That means in each second, we sample 44,100 data. For each data, we convert into discrete value, then we convert into digital value. We store that in the CD. Then we are going to recover the original analog signal from this a lot of data without any loss of information. That is the sampling theory. And we are going to discuss if you are given an analog signal, you are going to be able to determine the sampling frequency. Once you are given all this sampled data, you are going to be able to recover the original analog signal. For example, I give you all this data, analog. Can you tell me what is the value here? That is the reconstruction process. We have a scheme to do this. This is chapter 3. Any questions on that? So this chapter serves as this is the connection from analog into digital. In 315, we do not discuss this. Everything is analog. And in 316, we are going to briefly discuss this. Then we have this is bridge from analog to digital. Then later time, we are going to discuss digital communications. So now you can see the difference between the 315 and the 316. Right? The next chapter will be postcode modulation. So as in chapter 3, we are given an analog signal. We know how fast we should sample this data. Once we get this sampled data, this is discrete value. Discrete value means in time it is discrete. That means we have value here, we have value here, but we do not have any value in between. Analog data, that means we can have any value in between, at any time in between these two times. So that's continuous in time. So this one is continuous in time and also continuous in amplitude. That means this is 4, this is 3, then any value in between here, 3 and 4, we can choose them. For example, 3.1415. Right? Any number, so this is continuous. So this one continuous in time and continuous in amplitude. So that's called analog signal. Discrete signal is discrete in time only. Right? In time, we have this value, this value, this value, this value, this value. We do not have any value in between this time instant. But the value itself, the data, is continuous. That means this one equals 3, this one equals 4, this one equals 3, right? And any value, for example, this one, 3.14, can be chosen. Is possible. So this one is discrete in time and continuous in amplitude. Right? Now, digital signal is discrete in time. We know, right? For 1, 0, 1, 0. So only like here, 0, right? This is 1. Sorry, this is 1, this is 0, this is 1, right? Another 1, another 0, another 0. So 1, 0, 1, 1, 0, 0. It's discrete in time and also discrete in amplitude. We can only have 0, we can only have 1, we do not have 1.5 or 0.5. So this is called digital. Right? And how to convert this discrete value into digital? That is called postcode modulation process. Right? We are going to discuss this. And also you are going to use this concept in, I believe, CET316 later time. So AD and ADC, analog to digital conversion, and DAC, digital and analog conversion. Later time, if you do some senior project or anything, if you need to use AD and DA conversion, this are the concept you need to utilize. Okay. Any question on this? Corresponding to AM, FM, PM, the digital counterpart also have like PAM and PPM and PWM. You are several of you from CET. If you have do some CET project, you may know this pulse width modulation, and you will use this scheme to control the step motors. If you do senior project later time, you may also use this. So we are going to discuss the concept of it. Other concept that will be discussed are SNR, signal to noise ratio. You are given a signal. If we know the noise, then the ratio is just the signal divided by the noise. So for example, if the signal equals 100, if the noise equals 1, right, then that is the signal to noise ratio equals 100. That means the signal, the power of the signal is 100 times larger than the noise power. Usually this number is very, very large. For example, I'll give you another. This equals this. Or this one, if it's 0.1, then you have another 0 here. Usually these numbers are very large. It's not very convenient to write so large number. So what we do is we are going to use another one, so dB, which will be the concept will be discussed in first chapter. dB is just take the log of this base 10, then multiply by 10 or divide multiply by 20. So in this case, if it's the power, so we multiply by 10. So this log of this base 10 is 1, 0, 0, 0, 0, 0, 5 zeros. And this one will be equals 5, right? Because 10 to the power of 5 equals 100,000. So that's equals 1. So that is only not dB. D means deci. Right? This D means deci. This one is D. Right? And this D means 10 times smaller, the unit. So we have 10 before this. So this one, 10 times this, and that equals 50. So this signal to noise ratio will be equals to 50 dB. Right? You have a cell phone. When you make a call, you want a high quality. Right? So if you are very far away from the transmission tower, sometimes you hear a lot of noise. Sometimes you even drop the call. Right? The reason is most probably is the signal to noise ratio is too low. That means compared to the noise, your signal is too low. Or compared to the signal, your noise is too large. So either way, give you a smaller signal to noise ratio. If the signal to noise ratio is below a threshold, then you are going to the signal will be totally lost. Right? So this is here, and correspondingly there's a bandwidth. Right? You already know what bandwidth means, right? In 311. Right? If you are given a circuit, I ask you to find what's the bandwidth of the circuit. Can you do that? Yes or no? No? For example, I ask you, okay, what is the 3 dB bandwidth? Anyone has taken 311? Huh? All of you? So what does 3 dB bandwidth mean? Right? Suppose you have a circuit here. I don't care what's the details inside this box. Right? And we have an input signal, suppose xt here, and we have an output signal here. And this is in time domain representation. But usually we are going to use a frequency domain. For example, this one actually is a function of frequency. And this output is also function of frequency. Right? Now I will draw a plot here. This is the frequency, and this one here is the amplitude. Or, for example, the gain. Right? Or the transfer function is the y divided by x. The output divided by the input. The amplification factor. Right? So we can, okay, this is the G, or you may want to use this is A. But anyway, it is a function of frequency. Right? So for example, for DC, right? If frequency equals 0, you put your battery here, right? DC. Then this one, for example, okay, equal like this. And you increase the frequency, for example, the frequency equals 50 Hz here, and you calculate the gain, which is the output divided by input, still equals this. Okay? Then, okay, this is 50, okay, this is 100, okay, this is 1K, right? And so on, well, still equals at this point. Then we are going to observe with the increase of the frequency, this gain will decrease. Okay? After some time, for example, 1 meg, there's almost no output. So the gain will be equal to 0. So this is called the frequency response. You know this, right? Frequency response in 311 or 312, right? So the bandwidth is 3. Okay, now this is maximum. And we scale this one to 1. That means maximum equals 1. Right? All others will be less than 1. 3 dB means we choose the frequencies, for example, here, and the amplitude will be 3 dB less than the maximum. What's the 3 dB? 3 dB equals half. Right? So in power it is half. So this is 1, this is half, 0.5 here. Now the frequency from here to this point, that is called the bandwidth. It's called 3 dB bandwidth. Right? I believe you already discussed this concept in previous classes, and this is just a review. Right? Your communication system also has a bandwidth. There's a relationship between the signal-to-noise ratio and the bandwidth. These two are related. For example, if you have ultra-wideband communication system, your system is very good, ultra-wideband, then for the same quality, you can have a smaller signal-to-noise ratio. If you are in a remote area, your signal, for example, off the city, off the highway or somewhere, your signal-to-noise ratio is very, very small, it's very low, but still above some threshold, so you can still receive something. Then you need to have a wider bandwidth to have the same quality. So these two can be balanced. We are going to discuss the details later. The next one is compression and expansion. And expansion. Once we get all this discrete data, we transmit. We do not want to transmit all this data as they are. We are going to compress, then transmit. The reason for this is save resources. Okay, so we can transmit less number of data. But at the receiver, we need to expand the original data, the compressed data back into the original. We know, for example, you have large files, you want to copy to a disk or somewhere. There are lots of software to can compress the files. They use almost very similar schemes to do this. In communications, we also use this. What we are going to discuss is mu law and A law. We are going to use these two schemes as examples to discuss the compression and the expansion process. For these two, we have for each one we have two schemes. One is in the analog region, analog method. Another one is digital. So we have analog mu law, digital mu law, analog A law, and digital. We are going to discuss all of this. A typical example is once you sample the data, you got, for example, 12-bit of data. For example, if you want to transmit 10, this is decimal, 10. We convert 10 into binary. What is it? What is, okay, we do not use 10, we use 13. What is 13 decimal in binary? 1,
1, 0, 0.
0, 1, 1, 1, 0, 1, right? That is 8, that is 4, that is 1. So 1, 1, 0, 1, right? And 12-bit, so we are going to have 8 zeros before that. So for each discrete value, digital value, we are going to have 12-bit. So for each one, we sample all this. Each one is represented by 12-bit. And we do not want to transmit this 12-bit. Sometimes we can compress. For example, we compress this one into 8-bit. Right? You may think, okay, I just transmit all this part. So 1, 2, 3, 4, 5, 6, 7. Transmit this. Right? That's very straightforward. Right? But how about this one? If your number is 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, like this. Right? You say, okay, I don't care all these 4, I only transmit this one. So definitely we are going to have a large error here. Right? So we do not use this method. We have a special method, mu law, V law, to do this. But anyway, once we compress this data, we transmit, you receive, then we want to go back to the original data. That process is called expansion. So the examples we are going to discuss is from 12 to 8, and from 8 to back to 12. The last chapter is chapter 5. Is data transmission, right? And error detection, and error correction. Data transmission. Right? Now I transmit my voice. You receive my voice. Right? So that is one-to-one. When you make a call, you use that bandwidth. Usually there will be like a thousand of calls at the same time, transmit with the same frequency. So we are going to have some schemes to do this. It's called multiplex. That means transmit multiple signals with the same resources, for example, at the same time, or with the same frequency, or with the same wavelength. If we transmit multiple signals at the same time, that's called time domain multiplexing. It's called time domain multiplexing. If we transmit multiple signals with the same frequency, then that will be called frequency domain multiplexing. And the next one is wavelength domain multiplexing. You may wonder, frequency, wavelength, they are related, right? So how are both related? Frequency and wavelength. That is ET111, AC circuit. Frequency times the wavelength lambda equals what? Equals the speed of light. So this is a constant. Or the speed that the signal transmitting in that media, no matter it's cable or in the free space. So that is the speed of a signal in that media, not necessarily the speed of light. So F and V, wavelength, actually are related. So why we want to mention these two? They are the same, in some sense. Okay, this one usually means for light communication. For example, laser, optical transmissions. Because the frequency are very high, much higher than gigahertz, then we are going to use wavelength. For lower frequency, for microwave, millimeter wave transmission, or AM, FM, so we are going to use a frequency domain. We use this concept. So that's the only difference. Right? Next concept is line coders. For example, 1011. How are you going to transmit 1011? How to represent 1? In digital. 5 volt, yes, okay. So this is time, and this one is 1. 5 volt, for how long? So we set this one here, suppose this is 5 volt, so this is 1. The next one will be 0, okay, so that's 0 here. 1, 0. The next one is 1. Okay, the next one is 1 again. So 1, 0, 1, 1, like this. You know this, right? You saw this in your labs. 301 or 240 or something. How about this one? I'll use this one. Okay, 1. Before the end of the cycle, I will stop. This one, I won't stop until the end of the cycle. But this one is I stop before the end of the cycle. So I said this is 1. Okay? Then 0 is here. Okay? No difference with this one. But this one here also, this is 1, and then this is 1. Okay? This one is called non-return to 0. Means won't return to 0 until the end of the cycle. This one is called return to 0. Return to 0 before the end of the cycle. Right? I said 1, 0, 1, 1. Right? You said this is 1, 0, 1, 1. Right? Both works. Both work here. Right? So that is one way to do this. How about another one? I use this one to represent 1. I use nothing, okay, 0 to represent 0. Does this work? Every time you see this, you say, oh, this is 1. Every time you see nothing, oh, that is 0. Is it good? Yeah, that works. How about this one? I use this one to represent 1, but I use negative, like this, 180 degrees between these two, right? To represent 0. So each time you see this, that is 1. Each time you see this one, right, that equals 0. Is this good? Yes, it's also good. So we can see there are a lot of methods to represent these zeros and ones. That is called line encoder. Right? Each line encoder have different properties. We are going to discuss this in class, and you are going to have a chance to study more in the labs. Line encoders. The next concept is error detection. Right? So for example, now I transmit some numbers here. I said 1, 0. I transmit. You receive this one. You receive the 0, 0. Right? What I transmitted is 1, 0, but what you receive is 0, 0. Now, right, let's make this even simple. I transmit 1, but you receive 0. My question is, do you know if there's an error or not? For example, I said, okay, I said something. Now you hear, what you hear is 1, is 0. Now can you tell what you received is correct or not? Can you determine? I transmitted this from far away, right? You do not know. After this transmission, long distance, you received a 0. You believe. Now, can you tell me if this 0 is correct or not? You don't know, right? Maybe 0, you receive 0, which is correct. Maybe I transmitted 1, you receive 0, which is wrong. Why is it wrong? Because in the distance, in the media, for example, thunderstorms or anything, okay, damage your signal. So you receive 0. So that means this code has no error detection capability. You receive 0. You know nothing about this one is correct or not. That means we have a rule book or a dictionary. So 1 represents 1, 0 represents 0. Each time I see a 1, I transmit 1. Each time I see a 0, I transmit 0. But that's very simple. But at the receiver, no matter you received this or this, you have no idea it is correct or not, if there's error or not. So this code has no error detection capability. Does it make sense? Now I want my code to have error detection capability. For example, we can do like this. Each time you see a 1, you transmit 1 twice. Each time you see a 0, you transmit 0 twice. Right? Now, what you received is you received 1, 0. Do you think is this good or not? Is there error or not? Because in the rule book, there's no 1, 0. 1, 0 is not here. If the original data is 1, you should receive 1, 1. If the transmitted data is 0, you should receive 0, 0. We don't have any 1, 0. So there must be some error occurred during the transmission. Does it make sense? How about this one? You received 1, 1. Do you think there's error or not? Maybe no, which means I transmitted 1, 1, you received 1, 1. Or maybe yes, I transmitted 0, 0, you received 1, 1. Both are incorrect. That is possible, right? Right? So that means this one has capability to detect error, but it also has a limit. This one can only detect 1 bit of error. If you have only 1 error, yes, you can detect. If you have 2, no, you cannot. You received 0, 0. You received 1, 1. Maybe it is 1, 1 correctly transmitted. Maybe it's 0, 0. Both correct, are transmitted incorrect. So you don't know that. So this one has error detection capability. Does it make sense? We can repeat more, right? So each time you see 1, you transmit 5 times. Right? Each time you see 0, you transmit also 5 times. Now you received 1, 1, 0, 0, 0. Question, do we have error here? Yes. And can you correct the error? Which one is correct? Did I transmit 1 or I transmit 0? We don't know, right? Both are possible. But which one is more possible?
0.
This one. This one means that we have only 2 errors. This one is wrong, this one is wrong, right? So if I transmitted 0, you receive this one, you have only 2-bit error. But for this one, also possible, but you are going to have a 3-bit error, so which is less possible. So based on probability, you are going to determine this one, what I transmitted is 0. Right? So this one means this code, you can correct the error by yourself. Let's make this one a little bit more straightforward. Suppose you receive this one. Now you decide what is my transmitted data. 0, right? So oh, this one, this bit is the only mistake. It's the only error. So the transmitted. So you can automatically correct this one. But for this one, can you correct the we know, right? Suppose you receive this one, you know this is wrong. There's an error inside. But can you correct it? No. This one may be 0, 0, or maybe 1, 1. Both are possible. And they have the same probability. This one 50% of this, 50% of this one. So you totally know nothing about the correct data. So you can detect error, but you cannot correct error. So this is a very simple scale. That means we can design the data to be transmitted that make it has error detection capability and error correction capability. So that is good. The bad thing is, look at this. 1, you transmit 1, 1. 0, you transmit 0, 0. So you waste the resources by 50%. Or even worse, in this case, your efficiency is only 20%. You transmit 5 digits, which means only 1 digit. The The trick is, okay, you have a better error detection and even error correction capability. But the bad is the efficiency is extremely low. So this scheme is very easy to understand, but that's not a good scheme. Right? We are going to discuss even better ones. For example, CRC. Anyone knows this before? Or maybe you don't, right? Because everybody uses cloud storage. You do not copy a lot of files from disk to disk. Right? Before, if you copy disk from a lot of data from a hard disk to disk or something, sometimes you copy a file, say, okay, CRCL. That means that some data is wrong inside. Right? So this is a scheme. It's very useful, and we are going to discuss this in the class. Once we decide the code, for example, again, we take this one, we set file, this one 0, so 0, 0, 0, 0, 0, like this. If you received this, how we said, okay, we can automatically correct it with the limited capability. But how? With our eyes, we know this one looks like 1, 1, 1, 1, 1. Right? But we do not want to do this by hand with our eyes, because we transmit this data in each second like millions of data. You cannot do that. We use computers or the communication system itself will do this automatically. So we need to have a algorithm to do this. So how to do this? And we are going to discuss. And this is called coding, and this part is called decoding. This is the last chapter before the next one, which is hardwares. If we have time, we are going to discuss some hardwares, which is very simple. Right? You can read by yourself at the end of the textbook. Right? If we have time, we are going to discuss. Otherwise, you can read by yourself. So any questions about the topics? A little bit more details, what we are going to discuss in this class. These concepts are, I believe, are important. Right? If you believe you have some other ideas, topics you would like me to discuss here in this class, you can let me know. If we have time, then we can also discuss. Any questions on this? That is the topics we are going to discuss in this class. The next part is the course objectives and the course outcomes, all listed on the syllabus. That means after the class, after the final, what you are going to be able to do are listed here. You can use this one to test yourself. Next policy is homework. We are going to have a weekly homework. Some of you already have a class with me. You know the format of the homework. Every is a free response. No multiple choice, no yes or no, true or false. That kind of easy questions. Everything is free response. So that means you need to understand the textbook, the lecture notes, and everything. Then you need to write step by step the derivations and the final result, everything. We are going to have like totally 8 homework set. Each homework we may have like 3 or 4 questions. All questions carry the same marks. And all this homework count for 30% of your final score. Right? And attendance is 20%. And we are going to have a midterm test. We are going to have how many midterms do you want? Before I have only 1 midterm, but some suggest we have 2. I'll give you more chances, so I can have 2. But in the syllabus, I still says 1. So how many do you want? You want 2? 2. Then you can see This fundamentals, this part, that is the homework. This is the midterm 1, and this one, so that is the midterm 2. Then the last part is the final.
Yeah, I think we better that way.
Okay, that's way. Okay. Then in this way, I will change the skills. The attendance maybe. The attendance maybe, let me see, homework and midterm final will homework midterm will be 40% because there are 2. Each one is 10%. The final this one will be 30%, and the attendance will be 10%, and the homework will be 20%. So this gives you 100%. I will modify the syllabus. So we have 2 midterms. Each one is 20%. The homeworks add up all together is 20%. As usual, if you get 90 and above, that is A, and 80 and above is B. Sometimes I will occur. Collaborations. You are encouraged to collaborate with your classmate, with me. If you don't know how to do a specific homework, you can discuss. But when you submit, you need to write by yourself. You need to totally understand this, because in the test you cannot collaborate. For the homework, that's fine. So this 20% I considered for a long time. If it's only 10%, it's maybe too little. Okay, 30% because you can collaborate, so that maybe not good also. So I think 20% in our situation is reasonable. Any question on this? Otherwise, if you want to perform very well in the class, you need to come to class regularly and work hard on the homework and make sure you understand the theory behind each problem. You do not only want to copy others, you need to know why it should be like this. And to preview the materials, we have textbook, we have lecture notes. Better before coming to the class, you do like 10 minutes preview what we are going to discuss in the class. That's give you a better position to understand. And also to participate in class discussions actively. If we have asked questions, if you know it, just answer it. Discuss. Other support like writing, speaking. Okay, so you already know this. We have USM has a writing and speaking center, so we don't need this in this class. And extra resources. I'm more than happy to help students in any way, but you need to let me know you need help. I cannot force you to help you, right? So if you have, I know some of you, it's very good. Come to my office hours. I have office hours. Come to my office hours regularly. Ask questions about the lecture notes, the homework, everything. I'm very happy to do that. But keep in mind, do not wait until the last minute. Right? Well, tomorrow is the final. Today you go to my office. Okay, I cannot help you a lot, so that's too late. If you have math problems and the math department have like a math zone, I think they can help. And also our school has like I believe we still have a tutoring center on the second floor. Maybe not started yet, but if we have, then you can seek help over there also. Right? But keep in mind, I'm always there. Right? So in my office, so you can. Students are required to attend every class. We have attendance here. Right? Each recorded attendance has a point. Random quizzes may carry bonus. For example, I give you a quiz, then everybody get bonus. If you're not here, then you don't have that bonus point. Those bonus points can be can get up to 5 points, which will be added to the final. For example, you get this 10, this 10, this 10, this. Okay, final you get, for example, 19. So add up together, you get 89 points, right? Which is B. But in the bonus, you get 3 points. Okay, 89 plus 3, you get 92. That is it. Right? All the policies like incomplete, usually I do not give you incomplete. So if you here, you need to finish. And withdraws drops all the data on the university website. Check that if you want to drop the class, although I do not want you to do that. And this is required because you need to be here anyway. If you want to drop, withdraw to as early as possible. You can get your money back or something. It has deadlines. Academic integrity. You are seniors, juniors, right? So you already know that. We have listed the policy here. Take this serious. And professionalism, also all the policies listed here. You can read by yourself. Communication device, this one we need to enforce this. We already know use communication device is necessary, but not in the class. So I do not want you to make calls, receive calls in the class. If you bring your phone, your computer in the class, you need to turn it off. If your violations will, I think I have policy here, right? The first violation will give you one letter off. For example, you get A, but if you have one violation, you get B. If you get C, then you change it into D. The second violation will, you need to drop the class. So that's not my policy. I checked online. A lot of universities, they have similar policies. I don't want to be too harsh, but I think that's also reasonable. Electronic video and recordings are not permitted until if you have my permission. I record this for some purpose. So any questions? Computing devices, that means computers. We do not need to use a computer in this class. So don't bring the computer here. And especially do not do anything else. Website, emails, homeworks for other classes. So that's not allowed in this class. The ADA statement, you already know that. If you need a special request, there's an office on the website. So you send the request to them, and they are going to inform me directly. So we can't do anything based on the requirement. Okay, any other questions? We discussed the syllabus, the major topics in this class. We have labs in this class. The labs is 1 hour, the lecture is 2 hours. So we are going to have teamwork. We have 3 experiments total. We are going to start the labs. I want you to start labs after we discuss the content. So maybe we are going to start from the 3rd week or a little bit after that. So we are going to do this in teams. So how many do we have here? I hope everybody is here the first time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I believe we have 12 or something. Okay. Suppose we have 12. Yes.
I'm in your TVA section.
Okay. The labs is. Anyone knows what's the time for the labs?
11:30.
Okay. We have only one set of equipment for the labs. The lab is totally flexible. We don't have TA. If you really need help, come to me. So once we form a team, it is your responsibility to schedule the time that everybody on the team can meet, can do the labs. So that means TBA is only for example, when you schedule other classes, there is no time conflict. So that everyone is TBA. You have the code to the lab, right? If not, on the website you can apply for a code password, or I can open the lab for you. Who's in charge of the code? You know?
I believe I don't actually think we have the software for that.
Oh, we don't have software anymore?
No.
Oh, okay then.
The computer that was actually used to do that is in pieces. So.
Okay, then how do we do that?
I don't know.
Okay.
I will talk to Adams about that. I know he was the last one to be left in charge with that.
Okay.
So I'll talk to him, and then I'll let you know.
Okay, but anyway, the first 3 weeks we may do not have labs. Okay, later time I can open the door for you. So I will let you form the team by yourself, the team of 3. Is that good? Or you want me to do it? I can do randomly. No? Okay, so you can do by yourself.
Yeah.
We have 12, so team of 3. And I'm going to give you policies about how to do the teamwork. So everybody needs to participate. And if you are good, you cannot do everything. Just put the other 2 names on the report. That's not allowed, because this is teamwork. In this report, you need to write, okay, who did what, and all this. So I will base on those participation. That's give you a grade also. So 3. And you need to do the lab. So again, as we said, by yourself. You choose a time. Usually the labs, we said we have 3 labs, right? But each lab actually have like 2 or 3 small labs are combined together. The reason is that's more efficient. For example, if you do the sampling, right? The first one is do the sample. Okay, then you dismiss. The next day here, okay, you do the PCM. Then you still need to start from the sampling. Then you need to redo what you did yesterday, then do this one. So now combine together, so you just do from 1 to 3, then finish everything. So it's more efficient. Right? So that means you need a longer time. So maybe like 3 hours, 4 hours. Right? So when you schedule your time, consider this. 1 hour is definitely not enough. I will give you the format for the report. As we said, we have 3 labs, and we have 3 on the team. So usually, for example, suppose we 3 on the team. The first one, I will do the labs, the hands-on skills, and you, for example, record the data and process the data, and you can write the report. But when we in the lab, we need it all together, but we can separate it for different works. Right? So you write the report, put your name as a writer, you, and put the team members, and we do it together. And for the next lab, okay, then you do the labs, okay? I record the data, and you write the report, and we switch like this. So everybody get a practice of everything. Does it make sense? Right. And I need only 1 report for each team, for each lab. But you may get different scores. Depends on you are going to have peer reviews. For example, oh, that guy is very good. I did this contribution a lot, so I may give him more. So, any other questions? Oh, about the score. I will give you only 1 score for both lecture and labs. I won't separate. So this one is 100. The labs, I will give you 30. The total score is 30. So suppose you get perfect here, you get 100, but the labs you get only 10 out of 30. So both add up together, you get 111, right? 110. Make sense? Okay, 110 divided out of 130, then times 100%. What is this? Right? It is 91. Suppose then you get A on both. If it is 88, what is it?
85.
Oh, 85. Okay, so 85, then you get B on both. You can see the difference. It's 85 B on both, but if you separate, you get A here, you get F on the lab, right? So it's combined together. If you have an objection on this arrangement, let me know as early as possible, before the next class. So usually we just do like this. Okay, any other questions? We don't have a TA to help you in the labs. So you need to, I will post the lab menus on the website way before the lab. So my suggestion is you read the labs, the lab menus by yourself first, then you discuss as a group. Then before you go to the lab, you know what you are going to do. You know what you are expecting the result is. For example, I want to see the time domain signal of the sinusoid function. I can expect, okay, on the oscilloscope it looks like this. So then you connect everything, then you see this. Yeah, you know you are correct. Then you want to see the frequency domain signal Then you connect this one, you expect, okay, that will be a spike on the on the spectrum analyzer. Then you see, yes, it is correct, yes.
If we do have a question, our labs, we can't come ask you, right? Like, if we need assistance.
Yeah, you can. Yeah. But as we said, it's very flexible, right? If I'm there, then ask. If I'm not there, you can do the labs midnight, but I won't be here at midnight, right? So you can consider it, right? Any other questions? We still have like 18 minutes, so we need to. We discuss some fundamentals. Right? The first one is several trigonometric identities that we are going to use in this class. Right? The first one is the most important is a cosine function, cosine alpha times cosine beta. Anyone still remember this? No, okay? I don't blame you. That equals cosine alpha plus beta plus cosine alpha minus beta, and there's 2 here. So that is this is the first one. The second one is special case. For example, if alpha equals beta, so r cosine alpha squared 2, that one equals, look at this one, if alpha equals beta, alpha plus beta, that one will be equal to cosine 2 alpha, then plus, what's this one? Alpha equals beta, equals 0, cosine 0 equals 1. So that will be equal to 1. This is communication and not a trigonometry. So why this is useful? Now consider alpha is an angle or is a phase. So it will be equals omega times t, right? The frequency times time. And suppose alpha equals omega 1 times t and beta equals omega 2 times t. Then let's see what is this. So 2 times cosine omega 1 t times cosine omega 2t, then this one will be equals cosine omega 1 plus omega 2t, then plus cosine omega 1 minus omega 2t. Let's explain the physical meaning for this. This one is ideal cosine function with frequency omega 1. This one is cosine omega 2, frequency omega 2. These two sinusoid function multiply together. We are going to use a multiplier, right? In the labs, you're going to see this. It's called multiplier. So multiplier, we have one, you connect to here, another one, you connect to here. Right? So I'll do it like this. Right? So this multiplier, the one is here, another one is here. Right? So that's 2 input. And what we get is, we get this one. Frequency omega 1, frequency omega 2. Now let's see what we have as the output. The output also has 2 signals. One is this one, another one is this. So this one has a new frequency omega 1 plus omega 2. This one has a new frequency omega 1 minus omega 2. This frequency is higher than any of this. This frequency is usually is smaller. And we are going to use this one as a modulation process. So you have one signal, usually we call the baseband signal. Baseband means the signals you want to transmit. And another one we call carrier signal. carrier signal, this one here. Usually, this frequency, omega 2, is much larger than omega 1. Usually, it's 100 times larger than this one. Now, go back to the FM radio. The music is at most 20K. But the FM radio equals something like 90 meg. So, how many times of this? See, this one is 4,000 times, right? Even for, this is for FM. For AM, what is the frequency for AM station? You don't listen to AM. Right? The frequency band is from 535 to 1602 K. Even the lowest 535 compared to 20, still 20 times larger than this one. So this carrier signal is much larger than this one. Why? There's technical consideration we are going to discuss in later chapters. But here, we know this one is not. So this frequency is high, and this frequency is low. So usually, we are going to use, for example, filters. High-pass filters or low-pass filters, we can get no matter which one we want. So that is for this one. Another one is this one. Why this one is useful? Suppose you have an omega 1t signal, you receive, that is at the receiver end. Now, I will multiply by another cosine omega 1t, same frequency. So omega 1, I don't need to write omega 1, okay? I just use omega. So omega t times cosine omega t times cosine omega t. What we have here, we multiply together, that's going to be equal to half, that's 2 here, right? I'll move to this one. Then plus half cosine 2 omega t. Right? We are going to have this DC component here. And this one has even higher frequency. This way, we are going to use this idea to do the AM demodulation. So for example, if we have like MT here, then this one will be equal to half MT. We have all this one times MT. So you can see there's half MT, which is the base. Again, so you can see all, we are going to discuss the details later time, the techniques, and the technical point are from this map. So if you still remember all this, so everything is very simple. Any questions? We have another identity, which is cosine alpha plus cosine beta. That one equals equals 2 cosine alpha plus beta then plus let me see, times cosine alpha minus beta. This is again trigonometric identity. Now I plug omega 1, omega 2 inside. So cosine omega 1t plus cosine omega 2t. This one equals 2 cosine omega 1 plus omega 2t, then times cosine omega 1 minus omega 2t. These two add up together, we are going to have this one. We know from here, this signal multiplied together, we have a new frequency generated. So that is called nonlinear process, nonlinear circuit. So multiply is nonlinear. You are going to know this in 323. And this one, cosine omega t, omega 1 plus cosine omega 2t equals this times this. My question is, do we have new frequencies here? Looks yes, right? Actually, no, because this is multiply. Right? This one is not, these two are not new frequency. These two are, because this is the addition. Right? What we call this is called a bit. Right? This one is called modulation, it's called demodulation. This is a bit. So anyone play guitar? Right? If you have one string, that gives you one frequency, right?
Right.
If you have another string adjacent, it gives you another string. If you play these two at the strike at the two strings at the same time, actually you have two signals, but you add up together. In the, I don't know what's that called, okay, inside. What you get is this one. So what is this? Have you tried, if you play strike the two strings together, what is the sound look like?
A power chord. If you play them both together, it's a chord.
Their volume will change, right?
Yeah.
The volume will change. The frequency will change, the volume will change. Right? So that is called a bit. Right? For example, if these two frequencies are very close, because these two strings are very close, right? So omega 1, omega 2 are very close. So this one almost equal to 2 omega 1. It's high frequency. This one, omega 1 minus omega 2, because they are very close, so this one is very small. Right? Just very small here. So very small, close to 0, that means this one is very close to 1, right? But it is not equal to 1. But it's very close to 1. So you can consider this, if this one equal to 0, then this is equals 1. So that will be perfect cosine function. So it will like this. But this one is not. Right? Although it's small, but it also changes with time. So that means the amplitude is no longer a 1, it varies with time. So what we have is like this. Like this one. You can see this amplitude changes. The amplitude means the strength of the sound. So if you strike two at the same time, you hear the sound will change. It's no longer constant. Right? So this gives you the difference between the modulation and the demodulation. This is the modulation, this is the bit. They are different. Right? We have homework for you I believe for you to try to find the difference between these two. Right? The concept is important. So multiply together, that is the modulation process. Add up together is not. Right? Multiply together is a nonlinear process because we have a new frequency generated. And add up together, we do not have a new frequency generated. We still have the same frequency. Any questions on this? Alright, next one is discuss the power of the signal. Right? The average power. How to calculate the power? For example, if we have a cosine function, right? Like this one, what is the power of this one? A squared over 2, right? For example, if the voltage cosine omega t applied to a resistor, then that power will be v squared over 2r. Right? So the power of this sinusoid function equals a squared over 2. That's the second one. Next time we discuss two signals are orthogonal to each other. Orthogonal to each other means perpendicular to each other. Right? For example, if we have one vector, this is another vector, this is 90 degrees, right? That is V1, this is V2, okay? They are orthogonal to each other, perpendicular to each other. Right? That means V1 dot V2 equal to 0. We know this from physics, right? For example, if an object moving this way, right? So the D is in this direction, but your force is in here, F in this direction, then the work of the force down to the object is the work is F dot D. In this case, because they are perpendicular, they are orthogonal to each other, so that equals 0. Okay? So that is a vector for two signals orthogonal to each other. So one signal is this, another signal is this. These two orthogonal to each other. The definition is we multiply by this, we do an integral from A to B, from a domain. If this one equal to 0, multiply together, then do the integration because they are functions, not vectors. Vectors multiply equals 0. And this multiply, then we do the integration. Then this one equals 0. Then this is called these two are orthogonal to each other. Okay? Examples. Cosine m omega and cosine n omega, m omega t and cosine n omega t. You multiply these two signals. So they have different frequencies. Right? This is m omega, this is n omega. For example, this is 10 Hz, this is 20 Hz, or 30 Hz, different m. If you do this one from in one period, right, you do dt, right, you do the integration, you can do by yourself. Okay, we know if m not equal to n, this one equal to 0. Right? If m equal to n, right, then we divide it by the period here. Right? That one will equal to half. If m equals to n, this one equals half. That means any cosine function that have different frequencies, right? M omega, n omega, m n different, they are orthogonal to each other. Right? That means you do the integration, then dx, then this one equals 0. Right? If they are the same frequency, for example, cosine omega t itself times cosine omega t itself, this is the integration, right? dt, this one will equal to half. So signal to itself is not orthogonal. That's for sure. If there's only one signal, it's not orthogonal. Right? We are going to stop here, and we are going to. Today is Wednesday, right? So next Monday has no class. We'll see you next Wednesday.
Is that real?